So we're going to continue with substitution and elimination reactions. And in the last video, we discussed the SN2 process. That was a one-step process that was bimolecular. So there were two molecules involved in reaching the transition state. In this video, I would like to talk about the other type of substitution reaction, and that is the SN1 reaction. I'd also like in this video to discuss elimination reactions, so that'll come afterwards. In the SN1 process, we have a situation where we've got experimental evidence such that we'd expect a substitution reaction not to occur after learning about the SN2 process, because we have, a tertiary alkyl halide. We're just going to continue to use bromine because it's a good leaving group. We are using a tertiary alkyl halide, which we learned in the last video. SN2 processes do not occur on tertiary alkyl halides. We're going to be using a weak nucleophile. So instead of a basic or negatively charged species, we're going to just use a neutral molecule that just happens to have a lone pair of electrons, right? So the oxygen has a couple of lone pairs that can be used as a nucleophile to attack, right? And you get this product that you're not expecting, because you look at this and you think this was a substitution reaction, but SN2 processes don't occur on tertiary alkyl halides. So what happened? The other thing you get, if you end up using a chiral substrate, so that if the alkyl halide was chiral, if that carbon was asymmetric, you'd end up with two different stereoisomers. And in the SN2 process, you end up with just one stereoisomer, right? Because it's a concerted process. The carbon, we believe, does a backside attack on the carbon that bears the leaving group, and stereochemistry is inverted relative to your starting alkyl halide. In this particular situation, we have retention and inversion of stereochemistry if the carbon that's being attacked is asymmetric. So there's a couple of differences here. In the first place, we don't expect this reaction to occur, but then you do get this substitution product. So then what's going on? There must be a different pathway. So we have some experimental evidence for a new mechanism which will be unimolecular, meaning only one of those reactants is going to take part in achieving the transition state. In other words, only one of those reactants is going to take part in the slowest step, or in other words, the rate determining step. So we can draw, just like we did before, our little energy diagram. So relative to the progress of the reaction, what we find is we have our starting materials, we have some slow step, and then we have a second step, each with its own transition state, each with its own activation energy. So the first one, right, we can tell just by looking at the height, right, or the difference in energy. The energy barrier is going to be greater for the first transition state, right? So achieving that first transition state, that's going to be your slow step. So this right here, because it's taller, is going to be your rate determining step. So this is our slow step. And what we notice, so kinetically, is that if we double the concentration of the alkyl halide, we notice that the rate of the reaction doubles. But if we hold the concentration of the alkyl halide constant and double the concentration of the nucleophile, in this case it would be just water, right? Nothing changes for the rate. So that tells us that the alkyl halide is the molecule that's involved in the rate determining step. So that is, our rate law can be written like this. You got some rate constant times the concentration of your alkyl halide So what that tells us is that if we double the concentration or triple the concentration or 10 times the concentration of the nucleophile, like the water, or if we used methanol or something like that, then nothing's going to happen to the rate of the reaction as long as the alkyl halide's concentration remains the same. But if we double or triple or 10 times that, right, then we're looking at an increase in the rate of the reaction. So what you can do, and often in these cases, since doubling or tripling or whatever the concentration of the nucleophile doesn't affect the rate of the reaction, and in this case, we can use a weak nucleophile, then very often we make that nucleophile just be the solvent. And we do what's called a solvolysis reaction, so that you're using your solvent as a reactant, and it's in like 100 times excess because it's the solvent, right? Only, and we notice this is a substitution product here. We have substituted the hydroxyl group for the bromine. We notice that only tertiary alkyl halides undergo this type of mechanistic pathway, or we believe undergo this type of mechanistic pathway. So we don't see this on primary or secondary alkyl halides. So only tertiary alkyl halides undergo the SN1 process. Again, just like with SN2, this stands for nucleophilic substitution reaction, and the 1 stands for unimolecular, meaning the concentration of just one of those reactants is responsible for affecting the rate of the reaction. The other thing we notice is that this reaction is going to produce 2 stereoisomers. They don't have to be 50-50, but we do get 2 if you start out with an asymmetric carbon. So we get 2 stereoisomers. All of this is giving us sort of information about the mechanistic pathway. So 1 is going to be with retention of stereochemistry relative to the alkyl halide, and 1 will be with inversion if you have a chiral substrate. The example that I just showed you obviously is not chiral, right? The carbon is attached to 3 methyl groups, but if all 4 groups are different on that carbon and you have, a leaving group, you have a chiral carbon there, and there'll be stereochemistry associated with that. Here's the deal. So when we notice that we get 2 different stereoisomers coming out of this reaction, and we also notice this is happening on a tertiary alkyl halide, we immediately think, okay, first of all, this is not an SN2 process. The other thing is we have 2 things in the reaction pot, 2 reactants, and only one of them seems to be in charge of the rate of the reaction. So this is a unimolecular process. There's a lot of stuff that's different going on here. So this allows us to propose a different mechanism for what's going on. So unlike the SN2 process where we have a one-step thing that involves both molecules, we have a situation where we've got to take into account both the unimolecularity and the stereochemistry factors, because with the SN2 process, we end up with 1 stereoisomer, and that is if we have an asymmetric carbon, it proceeds with inversion of stereochemistry. What could happen that would allow this process to give us 2 stereoisomers? Well, what if you created a situation where you have your leaving group dissociate and you create a tertiary carbocation? So this is going to be your slow, or in other words, your rate determining step. If this takes off, we end up with a tertiary carbocation, right? This thing is a tertiary carbocation. Of all the carbocations, this will be the most stable. So we believe that this is a valid proposed mechanistic pathway. The leaving group leaves, and we create this tertiary carbocation. Here's where, when we did the review of Gen Chem, I was like, listen, you're going to have to imagine when we talk hybridization that instead of memorizing what, sp3, sp2, sp, all that entails, just use them as a visual. So in other words, that carbon is sp2 hybridized. It has 3 electron domains. What do we know about an sp2 hybridized central atom? It's trigonal planar, and the word planar is important. So we have an sp2 hybridized carbon. This is trigonal planar electron geometry. Why do we care? Planar means flat. And if this thing is flat like a little pancake, our nucleophile can approach from the top or the bottom. Unlike with an SN2 process where we're hitting an sp3 hybridized carbon, and we're hitting it from the back side, and the leaving group is going to be leaving from the front, and we're going to invert stereochemistry, this thing has the opportunity to be attacked from the top face or the bottom face. So that can come in from the top or the bottom. And if that happens, you can get 2 different stereoisomers, can't you? So this is going to be fast, because once you create your carbocation, it's going to be reactive, right? So this is just a proposed mechanism. We don't really know what's going on, but it's a valid mechanism based on the data. It helps to explain the stereochemistry. So now you have this situation going on, right, where you've had your neutral molecule attack a carbocation. Now that neutral molecule is attached, right, covalently, and there's an extra hydrogen there. So you can either have some more of your solvent come by and grab that proton and give the electrons back to the oxygen, and you get a tertiary alcohol. I'm not going to draw all the other stuff in the pot. You'll have the bromide in there. You'll have your protonated water, right? So you'll probably have like HBr aqueous, right? But we don't care about that. So we're concerned with the substitution product. So we have swapped out our leaving group for a totally new substituent. We have written a proposed mechanism that helps explain the unimolecularity. So that slow step only involves the dissociation of the leaving group. The nucleophile then comes in and attacks either side of the molecule because it's flat. So that helps to, it helps us to believe that that carbocation is floating around in the pot, right, in the rate determining step. And you can attack either side. You can create 2 possible different stereoisomers from that. So we talked about factors affecting the SN2 process. What factors could affect the SN1 process? Well, the first thing you want to think about whenever you're thinking, hey, like if you're the person in charge of, creating the method or, writing out, creating the reaction conditions, setting things up, right? You want to consider the leaving group. Which alkyl halide are you going to pick? Well, the leaving group is important, right? Because when you're looking at the proposed mechanism, you see that the rate determining step involves the leaving of the leaving group, right? The dissociation of the leaving group. So since that rate determining step involves the formation of the carbocation, the ability of the leaving group to dissociate is going to be important. The better able it is to leave, the easier the carbocation forms. So you're going to want to pick something with a good leaving group. That applies also to the SN2 process, right? Because in the rate determining step in the SN2 process, the nucleophile is attacking the backside of the carbon at the same time that the leaving group is leaving. So in both SN2 and SN1, the awesomeness of your leaving group is going to be important. So the ability of the leaving group to dissociate is important. So you're going to want to choose a good one. What makes a good leaving group? Well, same thing that made a good leaving group for the SN2 process. The weaker the base, or the more stable the species after it leaves, the better it is at leaving. So that's a nice common feature, right, between the two. The other thing that we notice about the rate determining step is it's the formation of the carbocation, this little positively charged carbon here. So the stability of the carbocation is going to be a big deal. So the more stable the carbocation is, the better supported that transition state will be, and therefore the faster the reaction, or the increased reaction rate, right? If you've got a well-supported transition state, that's really what you're after. When we say, like, how can we optimize these reaction conditions, you're thinking, like, how can I best support the transition state? It's that imaginary state between reactants and products. Don't you want to get there as quickly as you can? And don't you want to minimize the energy needed to get there? Well, what if part of that transition state involves the formation of the carbocation? You don't want to be hoping to make like a methyl carbocation. So this is insanely reactive. So that's going to be the least stable. Here we have a primary carbocation. That's the next least stable. You want to have a lot of groups on that carbon that bears the positive charge. By the inductive effect, if you think back to in intermolecular forces, right, and that those dispersion forces, you want to bolster, or support that carbon that has that positive charge. So you want more groups on it. You don't want just hydrogens, because they're, kind of almost good for nothing other than just like a proton, right? So they don't take up much space. They don't have a lot of electrons. They're not very useful if you're needing electrons for support. So the more groups you have on the carbon that bears the positive charge, the more supported it will be. So there's your secondary. So here's your methyl carbocation. Here's your primary carbocation. Here's your secondary. And then here's your tertiary. So if you can make one of these, this will be the most stable. And these are just, of course, generic, primary, secondary, tertiary. You could have a tertiary carbocation where instead of methyl groups, you've got these big other groups, like the more the better, right? The better the dispersion forces, the more stable it's going to be. So this is going to be the least stable. In chemistry, the least stable means the most reactive. And this down here will be the most stable. So in other words, you want to support an SN1 process. You want to create a situation where you're going to create the most stable carbocation that you can. It will be the least reactive. It'll be the lowest in energy, in other words. So there's so many different ways that you can view that, most stable, lowest energy, least reactive, whatever, right? The other thing that we notice is, once we get past that rate determining step and we think, well, what else is in the pot? The nucleophile, isn't it? And we've already decided that we believe that has really not much to do with the rate determining step, but it is part of the reaction, because without it, you don't get a substitution product, right? So, but since the nucleophile doesn't actually participate in the slowest step, or in other words, the rate determining step, its reactivity doesn't really have any effect on the reaction rate for this type of process, an SN1 process. In most cases, again, you can just use a neutral nucleophile. Instead of hydroxide, you can use water. Instead of methoxide, you can use methanol, right? And because the nucleophile doesn't participate, so we can just write this out as a reminder. So this doesn't participate. in the rate determining step. Therefore, its reactivity is kind of irrelevant. So its reactivity doesn't affect the reaction rate. So we can use a neutral, or in other words, a poor nucleophile, or a weak nucleophile, like water or methanol or ethanol or whatever. But we don't need, like, when we were talking about the SN2 process, we're saying, like, the smaller and more basic or negatively charged the species is, the better the nucleophile, if everybody, being compared is the same size. In this case, it's like you don't need to worry about having an awesome, powerful nucleophile because it's not really taking part in the slow step of the reaction. Once the carbocation is formed, your nucleophile, anybody with a lone pair of electrons is coming in hot for that thing, right? So, like, it can be just a neutral molecule that happens to have a lone pair of electrons, methanol, water, ammonia, whatever. And very often we use the nucleophile in an SN1 process as the solvent, or we'll use the solvent as the nucleophile because we can use these neutral molecules. And in that case, we have what's called a solvolysis reaction. So you take our token tertiary alkyl halide, why don't we just use this for a change. Bromine and chlorine, they're typically the ones that get used the most often. And instead of water, we can say, how about methanol? What would you get if you did this? So you allow this, and by the way, you got to put some heat into this. Usually for these, we just warm these up a little bit to increase the rate of the reaction. The formation of the carbocation is like, it's more stable as a tertiary alkyl halide. So to encourage the reaction along, we can increase the rate constant with an increase in temperature. So we end up creating what's called an ether. We haven't done these yet. We'll hit these functional groups coming up shortly. We'll have some leftover of this, or if we've protonated it, because it's come back to grab its hydrogen back, plus just the leaving group, right? So, but this right here is going to be your substitution product. So there's another factor affecting really all of these reactions that we're going to talk about, and that's the solvent. And I'd like to save that for after we cover elimination reactions, because there's a couple of good explanations as to like why you want to pick what you want to pick for your solvent. In the first place, you have to be able to dissolve your stuff. In an SN1 process, we can use the nucleophile, the neutral molecule, as the nucleophile and the solvent, right? And in that case, we'd be doing what we call a solvolysis reaction. So this right here, this is going to be the nucleophile, and it's going to double as the solvent. And when that happens, we have what's called a solvolysis reaction. But picking the right solvent for an SN2 process is going to be important too, right? Because we remember with the SN2 process that the nucleophile's concentration and its reactivity is going to also be part of the rate determining step. So it's bimolecular, right? The alkyl halide and the awesomeness of the nucleophile are governing factors for the rate of an SN2 process. With the SN1 process, really just the awesomeness of the leaving group and the stability of the carbocation that's formed are going to affect the rate of the reaction. So when it comes to picking a solvent for the SN1 process, usually people just pick whatever they need for the nucleophile and use that as the solvent. But like, what would you pick? What if you decided you wanted to do an SN1 process and you were like, well, what if I want to use a strong nucleophile? What if I wanted methoxide instead of methanol? Then you run into another problem. So if you decide to pick a really strong nucleophile for the SN1 process, you run the risk of an elimination reaction happening, because you run the risk of that nucleophile behaving as a base. And just like with the substitution reactions, we have a unimolecular and a bimolecular mechanistic pathway. So elimination reactions. Generally, in these, atoms or groups are removed from a reactant. And again, we'll use alkyl halides. And an alkene is formed. So instead of a substitution product, you end up with an alkene. You've lost a hydrogen and a leaving group, and you've created a double bond. So if you've lost the hydrogen, chances are it's because you involved that nucleophile as a base. So you found a nucleophile that is strong and negatively charged, and it behaved like a base. What do bases do? They rip hydrogens off of other molecules, right? So they deprotonate other molecules. And the hydrogen doesn't take its electrons with it, right? When it leaves, the hydrogen takes off with the base, and those electrons that were bonding it to the carbon that it was on, or whatever element it was on, they come down on the molecule they were on, and they stay there as either some negatively charged species, like if you took, an acidic hydrogen off an oxygen, if you took it off of a carbon, those electrons are going to come down, and you're going to form a double bond between two different carbons. The carbon that had the hydrogen on it that you just stole with the base, and the carbon next door, which in an elimination reaction has the leaving group, and then the leaving group leaves. So if that was confusing, let me draw out what I'm actually talking about here. So for example, I could have something like this, right? So I've got ethyl chloride or chloroethane, however you want to name it, and I've got hydroxide. So you can use that as a nucleophile, or you could use it as a base, right? It's basic, so it makes a nice nucleophile, but you would then run the risk of, instead of forming a substitution product, which when we did SN2, I could have drawn out the SN2 mechanism for this and created an alcohol, right? And that's what we did with SN2. What happens if the hydroxide decides to deprotonate this carbon? And you end up with this thing, plus this, plus this. So you think you're doing a substitution reaction, and you run in your analysis, mass spec, NMR, whatever, and you're like, wait a second, I don't have an alcohol. I've got a double bond in there. What just happened? So just like there are two nucleophilic substitution reactions, we've got two elimination reaction, or two mechanistic pathways, right? So let's start like we did with SN2. I'll start with E2. So the E2 reaction, the E stands for elimination, and the 2 stands for bimolecular. So in the E2 reaction, we have data that suggests that both reactants participate in the rate determining step. So the reaction progress diagram would look just like that of an SN2 reaction. There's one bump. It's a concerted process. What does that mean to us? Well, if you created an alkene, it means you lost the hydrogen off of one carbon, you made a double bond, and the leaving group took off. So it's one fell swoop, and it involves everybody, right? Both of these reactants. Bimolecular, concerted process. So that just means one step. So what could possibly be going on here? Well, I could take a tertiary alkyl halide. Unlike the SN2 reaction, we notice E2 reactions happening on tertiary alkyl halides. Now, if I were to take a tertiary alkyl halide and say, I'm going to do this reaction with a powerful nucleophile, and I'm expecting an SN1 process. I want to make an alcohol, right? This is what happens. Instead of using a weak nucleophile, you use a strong one. You end up making an alkene. The substitution process is therefore not favored for a tertiary alkyl halide when the nucleophile is strong. And then you get these byproducts. In order for that double bond to form, that hydroxide had to have taken the hydrogen off of one of those methyl groups, and the electrons come down, collapse between the two carbons, and then the chlorine leaves, and it happens all at once. So experimentally, we find in this particular case that the rate is going to be equal to some rate constant times the concentration of the alkyl halide and also times the concentration of the base. Remember, you can use a base as a nucleophile, but if you want to do a substitution reaction, you got to be careful. If the base is too basic, you're going to end up with an elimination reaction. Both reactants are taking part in the rate determining step, so we call this an E2 reaction. The proposed mechanism for this one fell swoop type thing is where we're going to, I'll just draw this rather suggestively. Draw the molecule prepping the hydrogen for attack. And we're going to take our base. So here's a base behaving as here's a nucleophile and a base, right? It's a base that could behave as a nucleophile, but here it's going to act like a base. In one step, we snag that hydrogen. The electrons that bond that hydrogen to the carbon come down and form a double bond between the two carbons, and the leaving group leaves. So it's one step. And you get your alkene. Plus your other stuff. So that's the proposed mechanism. It's all one step. The base removes a proton. So let me write this in a different color. There's some terminology here that is important to mention. Your base is going to remove a hydrogen from what we call a beta carbon. What is a beta carbon? A beta carbon is a carbon adjacent to the carbon that bears the leaving group. So it's the carbon that has the leaving group, its next door neighbor carbon is the beta carbon. So the carbon that bears the leaving group is the alpha carbon, and the carbon next door is the beta carbon. So the base removes a hydrogen from the beta carbon. That's one step. As the hydrogen is removed. The electrons that it shared with its carbon will move toward the carbon bearing the leaving group. And as that happens, the leaving group dissociates. All in one step. So that's our E2 process. Again, just like SN2, it's a one-step process. The difference between the substitution and elimination is in the substitution, we're going to actually swap out a leaving group and a nucleophile. So that nucleophile will add to the carbon that had the leaving group on it. In the case of the elimination, your nucleophile, if it's basic enough, is going to deprotonate the beta carbon. That is the carbon adjacent to the carbon bearing the leaving group. And those electrons are going to collapse between those two carbons, right? You'll end up creating a double bond, and the leaving group will leave. So there's some similarities there between the SN2 and the E2 process. Likewise, there are some similarities between the SN1 and the E1 reaction. So as you might guess, this is not going to be a concerted process. This will be a two-step process, right? This will be unimolecular, as its name implies. This will be two steps. So I think in some cases, people get confused the fact that we call it an E1 reaction or an SN1 reaction, and it happens in two steps. The reason we call it E1 and SN1 is because we're talking what molecules take part in the slowest step of the reaction. It doesn't refer to how many steps there are, right? Because with SN2 and E2, it's one step, but it involves both reactants. So I've run into situations where people get those confused. Just like the SN1 process, this happens in two steps because, as you can imagine, this is going to be the creation of a carbocation first, right? So this could be our proposed mechanism where that leaves, and that's our rate determining step. It's the creation of that carbocation. And then in comes, maybe I should draw this just a little bit better. Make that a little easier to grab. In comes what we would think is a nucleophile, so we'll just use water. So we think we're getting a substitution reaction happening here, and we get a little of this. We quench that positive charge. And you can write this like this if you like, because it'll probably just be the hydronium ion, right? And then Cl minus. Or you could say HCl aqueous. Fine, no one cares about that stuff. It's really your elimination product. So you get this alkene. So the rate of this is going to be equal to some rate constant. And it seems that only the alkyl halide concentration affects the rate. Again, it doesn't matter what nucleophile you have. And in fact, if you had used a strong nucleophile, you'd still have the alkene. It would just be an E2 process. But if you come out with an alkene, you have an elimination process, right? If you come out and set this thing up such that you think you're going to make the substitution product, so in other words, you think an SN1 is going to happen. So you use water because it's weak, right? And then you get some alkene. You're like, what just happened? I thought I was going to get substitution. I used a weak nucleophile. You do have the chance of creating some alkene. You, in this case, would create, if you used a weak nucleophile in a situation like this with a tertiary alkyl halide, you would create both elimination and substitution products. And the substitution would be favored in this particular case. If you started out with a tertiary alkyl halide and you used a strong nucleophile, since substitution is not possible, you would end up only with the elimination product. So in this particular case, again, you've got your leaving group dissociating, you form your carbocation, and then in this case, the water is going to act as a base. It's going to remove a proton from the beta carbon, and you're going to form your alkene. There are some important things to recognize with these substitution and elimination reactions is that in the case, so since the rate determining step of an E1 reaction involves only the formation of the carbocation, the rate of this reaction will depend both on the ease with which the carbocation is formed. In other words, like the ease with which the leaving group dissociates, and also the stability of the carbocation. So it's important to note that primary and secondary alkyl halides do not undergo E1 reactions. They do undergo E2 reactions. So you can create an alkene with a primary or a secondary alkyl halide. It's one-step process, right? You're not creating a carbocation in the rate determining step. So let's talk a little bit, since we have alkenes here, about the products associated with the elimination reaction. And then we'll talk a little bit about the factors affecting them. So first of all, since we're talking about alkenes, let's discuss the regioselectivity. So regio really just stands for region, like the place on the molecule that's going to react. In an elimination reaction, we know that the base is going to remove a hydrogen from a beta carbon. But what happens when you have two options or three options for beta carbons? What if you have an asymmetrical alkyl halide, right? So what if I have something like this? Now, in this particular case, I could deprotonate that carbon, or I could deprotonate this carbon, right? So I come in with a base. So I just use methoxide, and I get this molecule, and I get this molecule. This one is going to be, according to the data, the major product, meaning you'll get both, but the ratio will favor that one, and this will be your minor product. So here is a beta carbon. And here is a beta carbon. And to get both of those products, you'd have to deprotonate either one of those, right? So notice how the major product is formed, and this we notice time and again, this major product is formed when the hydrogen is removed from the beta carbon that is more heavily substituted. So it looks like the more stable alkene is the more heavily substituted alkene. Our data suggests, so we can plot this again if you like. Some people like seeing these and some people are like, this does nothing for me, but I'm just going to draw this out for you. We're going to plot both of these on the same curve. And for this, we're going to, for example, choose just an E2 process. So we only have to do one activation energy, right? And I'll do this in 2 different colors. So we could just, I guess, pick green for one of them. So our reactant starts out over here. And we end up with this. And we notice that we start out in the same spot. For the other product, right? Same reactant. Exaggerate that just a little bit. This right here, this orange curve, describes the reaction progress for the more stable alkene. It's lower in energy, or its transition state, or its activation energy is lower. The more stable alkene, we believe, is the more highly substituted alkene, number one, because you can actually measure the ratio of these. This is us just trying to work back and rationalize why this might be happening, because it happens time and again, right? Energetically, why might this be happening? Well, maybe because the more stable the alkene is, the more highly substituted it is, ends up being the major product because the transition state leading to its formation is lower in energy, right? So anytime something can happen at a lower energy versus a higher energy pathway, it's going to pick the lower energy pathway. We notice that time and again as well. So we believe that this could be the reason. The transition state is lower in energy, or the activation energy is lower. And then the energy of the product is lower, which also speaks to its stability. So the more heavily substituted the alkene, the more stable it will be, and that will end up being your major product. The other thing that we have to concern ourselves with would be stereochemistry. And I should mention, I don't know if your book talks about this, but this right here is Zaitsev rule. I always forget how to spell this person's name, but like Markovnikov's rule, we have Zaitsev's rule. So the more heavily substituted alkene, or the more internal the alkene, the more stable it is. We also have to concern ourselves with stereochemistry. So not just regiochemistry, but stereochemistry. Regiochemistry is like, hey, which hydrogen are you plucking off? Like, what carbon's getting deprotonated? That's the region of the molecule that's reacting. Stereochemistry is like, what kind of stereoisomers am I going to get here? Cis trans, EZ, that kind of thing, right? A stereoselective reaction, or a regioselective reaction, is a reaction where one isomer or one product is formed in a greater amount than the other. So if somebody says this is a stereoselective reaction, they're telling you you're going to get one stereoisomer formed in a greater amount than the other. Something is going to be favored over something else. So again, let's just stick with one-step process, and we'll do another E2. We'll do regiochemistry first, and then we'll use the same reaction, but I'll pick the major product to illustrate the stereochemistry. So we'll take something like this. Some base. So this is ethoxide instead of methoxide. And we're going to get a couple of products here, aren't we? So you have the option. Again, we have this as a beta carbon and we have this as a beta carbon. So if we deprotonate the one on the left, that carbon loses a hydrogen and the bromine from the other carbon, and we create this alkene. You will also have the opportunity to deprotonate the other carbon. And you get that. This is your major product. It's more heavily substituted. Here's your minor product. But notice if we are looking at the two carbons that are doubly bonded, they each have a hydrogen, but then one of them has a methyl group and the other one has an ethyl group. So now we have the issue of do you make cis or trans isomers? So we have a stereochemistry thing going on. And I'm going to use the major regioisomer for this illustration. So I'm only going to use the major product for this. So we have, oops, redraw the reaction. So now just using that major regioisomer, let me move this up a little bit. Okay. I have a carbon that has an ethyl group on one side and then a hydrogen. So see how we're expanding the structure now? The other carbon has a hydrogen and then just a methyl group. I could also draw it like this. Where both groups are on the same side of the double bond. In this case, I have the trans isomer, and in this case, I have the cis isomer. The trans isomer is our major product. It puts the two bigger groups farther away from each other. So they're on opposite sides of the double bond, whereas the cis isomer puts both groups on the same side. Somebody might be sitting there going like, so why is that cis trans? When does EZ come into play? All right, let me show you. You get EZ when you have both carbons that have, like one of the carbons may have a hydrogen and an R group. The other carbon is going to have like two different R groups, right? So then you have to pick the bigger groups. So for example, we could say, we'll put an ethyl group over here. We have our carbon, a methyl group, our leaving group, and say like another ethyl group. In this case, we're going to, we'll do an E1. How do you know? Because you have a weak or a neutral molecule there. That's not a base. It can be basic, right? But if you end up with the alkene after this, it was an elimination reaction and the methanol acted as a base. So that's neutral. I have the option to make, so I'm going to deprotonate where? So I could either deprotonate this carbon, or I could, well, we're not doing regiochemistry here, so let's stay on track. I could make this, oops. Make sure I did that right. 1, 2, 3, 4, 5, 6. No, I screwed that up. Sorry, I added an extra carbon. It's pretty easy to do. So if I have deprotonated here, there we go. Or I could have deprotonated and created this isomer where I put the methyl groups on the same side and I move the ethyl group down. So in this case, I have the biggest group on the left-hand carbon is going to be that. The biggest group on the right-hand carbon is going to be that. They are on the same side of the double bond. We call that the Z isomer. Over here, I have the biggest group on the left-hand carbon here, the biggest group on the right-hand carbon there. This is the E isomer. This ends up being, for all the same reasons with the cis-trans situation, the major, and this ends up being the minor product. So do you see the difference when you're calling something cis-trans? Both carbons have a hydrogen and then an R group. In the situation where one of your carbons, or say both of them, they all have different R groups, you got to pick which one is bigger, which one has bigger mass. It looks like cis-trans, but you're not really talking about a cis-trans isomer. You're talking about like the size of the R groups that are actually on the carbons that are doubly bonded. Like where are those relative to each other and the double bond? So what kind of factors? Because we have factors affecting the substitution and elimination reactions, what about, or I'm sorry, the substitution reactions, what kind of factors are going to affect the elimination reactions? Well, you have to look again at all the stuff that's involved in the reaching, the transition state, or all of the molecules or the species involved in the rate determining step. And then also solvent and all that kind of stuff too. So E1, E2 reactions. First thing that comes to mind is going to be the alkyl halide reactivity, isn't it? In an E2 reaction, you can have primary, secondary, and tertiary alkyl halides reacting. Tertiary alkyl halides react the fastest. Secondary alkyl halides react second fastest, and primary alkyl halides react the slowest. With an E1, you have to think about what's going on. You have to make the carbocation. So the carbocation stability is a factor. Primary and secondary alkyl halides do not undergo E1 mechanistic pathways, only tertiary alkyl halides. And then E1 conditions mirror SN1 conditions, so neutral or weak nucleophile. So if you're going to set up a reaction with a tertiary alkyl halide under SN1 E1 conditions, you will get some of the alkene, but the majority of the product, if these are competing with each other, will be the substitution product. The other thing you have to consider is the awesomeness of the leaving group, the ease with which this leaving group departs. So the ease with which the leaving group dissociates. And that is, how stable is the species that leaves? So weak bases are good leaving groups. You're not going to eject something that's more highly energetic, right? That doesn't make any sense. If you're going to be ejecting something that's more highly energetic, you're making a more reactive species. Doesn't mean it can't happen, just means that it's unlikely. And the leaving group that is weaker when it leaves is going to be attached to the more reactive alkyl halide. So in other words, if you have some group with an iodine attached, that's going to be your most reactive. Then the bromine, then the chlorine, and then fluorine. So this will end up being the most reactive alkyl halide, and this will be the least. That means iodide is a better leaving group than fluoride. It's a weaker base. What happens if, because we've been talking all along about, like, you could set this thing up under, SN1, E1 conditions, and then, you're going to end up mostly with substitution products. So I'm hinting at something here. What if we have competing reactions? So, in other words, substitution versus elimination. So, some things that we know, or we believe that we know anyways, SN2 or E2 are going to be favored by the presence of a strong, like basic, as in negatively charged, right? Nucleophile, or I should say also highly concentrated, right? Because in the rate determining step, we have a bimolecular process. So not only the concentration of the alkyl halide, but also the concentration of the nucleophile or the base is going to affect the rate of the reaction. So a strong, in other words, a basic, like a negatively charged, highly concentrated nucleophile is going to speed up an SN2E2 process. Something else that we have noticed from the data is SN1, E1 are favored by a neutral or a weak nucleophile, like in other words, like a weak base, like water or an alcohol or something like that. We also noticed that primary and secondary alkyl halides do not undergo SN1 or E1 reactions. And we just believe this because in the proposed mechanistic pathway, the rate determining step involves the formation of a carbocation. The more stable the carbocation, the faster the reaction. Primary and secondary alkyl halides produce primary and secondary carbocations, which are more energetic. They're unstable, right? So they're not as stable, they're not as unreactive, they're not as low in energy. And so primary and secondary alkyl halides don't undergo reactions in which their carbocations would need to be formed in the rate determining step, right? So in other words, tertiary alkyl halides are where it's at for SN1, E1 processes. You can, even though we can favor them by using a poor nucleophile, so even if we set up a reaction with a primary or a secondary alkyl halide with like water or methanol or whatever, or some weak base, even with their high, so if you're setting that up like an SN1 E1 reaction, you're taking that nucleophile, and even if it's like neutral, you're jacking up the concentration. We typically do these reactions as solvolysis reactions. So if you're increasing the concentration of the species that could act as a nucleophile or a base, even if it's neutral, you're then tipping the scales in favor of SN2E2, right? Because the nucleophile concentration actually takes part in the rate determining step for those processes. So all these little dots that we're trying to connect or tease apart, right? They all matter. All these little pieces of the puzzle. E2, if you're curious, and SN2 compete with each other. So experimentally, we have to decide how we can tip the scales in favor of one over the other. The first thing I can think of is the type of alkyl halide that you choose can favor one of these over the other. So for an SN2, we notice that the reactivity of the alkyl halides go primary is more reactive than secondary, which is more reactive than tertiary. And for E2, we notice that tertiary is more reactive than secondary, which is more reactive than primary. So if I have a primary alkyl halide and a highly concentrated basic, right, or strong nucleophile, I'm probably going to be favoring the SN2 process. If I have a tertiary alkyl halide and I have a high concentration of a strong nucleophile, so negatively charged species, then I'm going to favor the E2 process. Secondary alkyl halides are kind of a drag, right? Because you'll get both substitution and elimination product. But here's the deal. Experimentally, it's been found that the elimination product is actually favored by just a little bit. So primary alkyl halides favor SN2, tertiary alkyl halides favor E2, secondary alkyl halides favor both, with E2 being the major product if you were to get a little mix. And tertiary alkyl halides don't undergo SN2 reactions, so I should probably put like one of those. This is probably not going to react. Or it's not going to follow an SN2 process. If you end up with substitution product, it probably underwent an SN1 process. The SN1 and E1 processes sort of rely on the dissociation of the leaving group to form a carbocation. So the stability of the carbocation is going to be important for both of those reactions. So if you have a situation where your carbocation is stable, SN1 and E1 are both going to be favored, you will end up favoring the substitution product. So like if you were reacting a secondary alkyl halide under SN2 E2 conditions, the elimination product is favored. If you're under SN1 E1 conditions, your carbocation is stable, so like you have a tertiary carbocation, right? Because primary and secondary don't undergo SN1 E1 processes, then the substitution product is therefore going to be favored. And that's kind of fortunate because under the SN2 E2 conditions, only with a tertiary alkyl halide, only the elimination product forms. So for example, if we take a tertiary alkyl halide, and we allow this to react with methanol in excess, so in other words, we have SN1 E1 conditions. When you see that SN1 E1 conditions, it means you have a neutral nucleophile used in massive excess, so probably the solvent, a neutral or a weak nucleophile, right? And what you get is this. I'm only going to draw the major organic products here. You also, so there's your substitution product, right? You also get some of this. So there's the elimination product and the substitution product. The major product would be this. Minor product would be that. If you were to take this same molecule, I'm going to get lazy and just duplicate this. And instead of methanol, I use methoxide. So now I've got a strong basic nucleophile. SN2E2 conditions, we only see this. And no substitution product. So it's fortunate that under SN1 E1 conditions, if you have a tertiary alkyl halide, your major product is the substitution product. Fortunate as in we can get to the substitution product under those reaction conditions, because both SN1 E1 and SN2 E2 would favor would produce some of the alkene. So if you want some substitution product from that particular alkyl halide, you want to choose the SN1 E1 reaction conditions. And when I say reaction conditions, it's not just the nucleophile, it's not just the alkyl halide. If you're not doing your reaction in a solvent that's also acting as the nucleophile, so in other words, like you're going to pick two different reagents and you're going to dissolve them in a separate solvent, then you have to consider the solvent as well. So this is where we're going to lean just a little bit back on some of our Gen Chem stuff. And some of these intermolecular forces of attraction. So if you have a reactant that participates in the rate determining step and that reactant is charged, like for example, in the SN1 E1 process, you have a carbocation, right, involved in your rate determining step, and it has a charge on it. Or what if you have an SN2 E2 process and your nucleophile is basic and it has a negative charge? That's what we're talking about. So some species with a charge on it in the rate determining step. So if you got that going on, increasing the polarity of the solvent is going to decrease the reaction rate. Why? Because the charged species is going to be busy interacting with the solvent, right? But a charged reactant is insoluble in a nonpolar solvent. So now what are you going to do, right? So if you have a charged species involved in the rate determining step, a polar solvent will decrease the reaction rate. This is another reason we like to use the solvent as a nucleophile in a solvolysis reaction, because in an SN1 E1 process, you have your carbocation in the rate determining step. It's a charged species. It's going to be busy interacting with the solvent. Wouldn't it be great if that solvent was also the nucleophile, right? So that's like, ooh, good idea for an SN1 E1 reaction. You want to choose a polar protic solvent and let it be the nucleophile or the base, right? If it's E1. So let it behave as both the solvent and the base. So if you have that charged species in the rate determining step, you have a polar solvent intertwining with that charged species, then if the solvent is not the other reactant, you are now tying up the species involved in your slowest step with the solvent. It's busy chatting with the solvent instead of reacting with the other reactant, right? So you're going to decrease the reaction rate because it will be busy with the charged species. You create a carbocation that's involved in the slowest step of the reaction. If you're choosing a solvent that is not also going to be a reactant, then your charged species, that carbocation that's involved in the slowest step, is going to be hanging out. Intermolecular forces of attraction are going to pull it toward the polar solvent. If you're smart, you'll let that solvent also be the other reactant. And in a sneaky little way, you end up increasing the rate. So what you want to make sure of, since in the SN2 E2 reaction, you come in with this reactant, so it's bimolecular, so already both reactants are involved in the slowest step. One of them is the nucleophile or the base. And if you're comparing, nucleophiles that are comparable in size, a more basic molecule or ion is going to be a better nucleophile. That's going to be a charged species, right? A negatively charged species. So if you choose a polar protic solvent with your SN2E2 process, then you're busy tying up one of the reactants with the solvent, and it is then therefore not busy reacting with your alkyl halide. But what if you could be sneaky about it and you could choose a polar aprotic solvent? Because here's the deal. If you have a charged species and you choose a nonpolar solvent, it's not going to dissolve. So that's its own conundrum, right? But if you choose a polar protic solvent, then you have your charged species tied up in hydrogen bonding, right? Or if you have some kind of like salt in there, like sodium methoxide, and you want the methoxide to react, then you've got ion dipole forces. That's going to stink. So you want to choose a solvent that's polar, so your stuff dissolves in the first place, but you want an aprotic solvent. And that will tie up any spectator ions, like potassium or sodium or whatever. So any spectator cations. And will allow your charged species to dissolve. So this can get a little tricky with SN2 E2, because very often we'll have like hydroxide or methoxide or ethoxide or something like that, right? Where you've got a negatively charged species acting as either a base or a nucleophile. And those species that are negatively charged are not going to dissolve in something like benzene, right? Or like, carbon tetrachloride or something that's non-polar. So how do you get a solvent that's polar and won't bother like it's not going to hold up your reacting species from actually reacting? Let me show you a couple choices. One of these things is awesome. You could dissolve rocks with this stuff. So we have DMSO. This is dimethyl sulfoxide. So up here we have like a partial negative charge on our oxygens, right? That's going to create an ion dipole interaction. We'll just use potassium as a spectator cation, for example. That's going to coordinate, right? The partially negatively charged oxygen is going to coordinate with the positively charged potassium ion. And that came from, say, like potassium methoxide or whatever, so that this portion of the salt, where this was potassium methoxide, this is now free. It is dissolved because it'll dissolve in this polar solvent, but it's free to react. So you're probably sitting there going, well, if you have a partial negative charge on your oxygens, don't you have a partial positive charge on your central atom? And the answer is yes. Here's the thing, though. It's sort of stuck in the middle of the molecule. So the anion that you want to use as either the base or the nucleophile is not quite as attracted to the center of that molecule, right, as the potassium is to those outer partial negatively charged oxygens. So this will dissolve your reactant, but it won't hog up all its time, right? So now that methoxide is free to act as a base. DMF, so this is DMSO, dimethyl sulfoxide. DMF, we haven't gotten to amides yet, but when we do. We got this. This is dimethyl formamide. This is another situation where we have, and in this particular case, we have a resonance structure. Where now we can coordinate with the cation, right? And it will dissolve our anion. But it's not going to hog up all of its time. So this will be dissolved again. But free to react. In each of these cases, we have a polar solvent. There's polarity about it, right? Partial positive charge, partial negative charge. There's no proton available. A polar protic solvent, so let me write that as an example under here, would be like methanol. It's a polar solvent, but it has a hydrogen that you can use for hydrogen bonding. So methanol or water is considered polar and protic. Polar aprotic, A means without. It means you got a polar solvent, but there's no hydrogen directly attached to the more electronegative atoms. So you're polar and you can dissolve something that shares similar intermolecular forces with you, but there's no proton there. You're not gonna protonate, that methoxide and make methanol. You're not gonna poison your reactant, in other words, with these intermolecular forces or by protonating it, right? So anyways, solvent considerations, pretty important for SN2E2. SN1E1, you kind of already set yourself up to use a polar protic solvent because you're using like a weak base or a neutral molecule as the nucleophile or the base anyways, right? So that's kind of, and it's already in excess. So you kind of want to make sure that that's not super basic or super nucleophilic, because if you're going to jack up the concentration, then you're favoring the SN2E2 process. If you're dealing with a tertiary alkyl halide and you want the substitution product, you definitely don't want to favor the E2 process because that will eliminate in a second. You get the alkene, right? So you have to know your alkyl halide, know your leaving group, know your solvent, and fixate on the rate determining step in the process so that you can set up your reaction conditions to favor the process that you hope will occur.